Hello everyone. Let us discuss about line coding techniques and digital formats. Now, encoding is the process of embedding clocks into a given data stream and producing a signal that can be transmitted over a selected medium. So from the transmitter side, what we will do is that because we have to transmit digital information in the form of a bit stream, so we will apply some kind of coding because at the digital information has to travel through the channel. Channel will introduce noise and will distort the signal, and there will be distortions, of course. Then at the receiver, we should be able to detect symbol by symbol period the bit information that is coming from the transmitter side. So at every symbol period, the same bit information should be detected. So for that, we have to introduce certain clocking strategies at the transmitter side, and that's what we call as encoding, so that the proper detection can be done at the receiver. So coding is the process of embedding clocks into a given data stream. Now the transmitter is responsible for encoding, that is inserting clocks into data according to a selected coding scheme. So it is the responsibility of the transmitter to include the encoding, that is clocks will be inserted and under a selected coding scheme. So what is the meaning of selected coding scheme? The transmitter, while doing the encoding under a given strategy, the receiver will also know that the same strategy, that particular strategy was used at the transmitter, so that receiver applies the same clocking strategy to detect the digital information. Receiver is responsible for decoding, that is separating clocks and data from the incoming embedded stream. Now the systems that use coding are synchronous systems. Why they are synchronous? Because that's the kind of clocking strategy is being applied here. So once the clock is there in the system, then the systems will be called as the synchronous systems. We must encode data into signals to send them from one place to another. There are four possible encoding techniques that can be used on data. One is digital to digital encoding, digital to analog encoding, analog to analog encoding, and analog to digital encoding. So I will discuss in detail this digital encoding and this um, uh, analog to digital decoding, right? As far as this part of digital to analog and analog to analog encoding is basically your analog modulation schemes like analog modulation or frequency modulation and phase modulation. I will not go into the details of analog to analog modulation schemes or encoding schemes. Digital to analog also, I will not go into detail because that's a separate topic in which the amplitude shift keying, the frequency shift keying, phase shift keying, quadrature amplitude modulation kind of encoding techniques will be used. So I'll be mainly concentrating on digital to digital encoding schemes in this lecture, and I will also discuss some part of analog to digital encoding schemes. All right, the binary signals created by your computer are translated into a sequence of voltage pulses that can be sent through the transmission medium. So whatever the binary signals are created by the computer in the form of zeros, they need to be sent through the channel, right? Excuse me. They need to be sent through the channel in the form of voltage pulses. Now, binary signals have two basic parameters. One is amplitude and the other one is the duration. So as the number of bits sent per unit of time increases, as we are increasing the number of bits per unit time, basically that will be called as a symbol period. The bit duration will also decrease as we are increasing the number of bits in one symbol period. So bit duration allocated to each bit will be decreasing because the symbol period will remain constant. The three most common methods of encoding used are unipolar, polar, and bipolar. So let us look at various encoding schemes. All right, so this is digital to digital encoding. the process of converting this digital bit stream into waveforms, into some kind of pulses, is known as line coding, right? And let us talk about the unipolar encoding first. So this is the simplest and most primitive type of encoding used is unipolar encoding. So typically one voltage level stands for binary zero. So let's say this is plus 5 volt or plus 10 volt, plus 3 volts, plus 2 volts. This will correspond to 1, and a 0 volt will correspond to a 0. So that means typically one voltage level stands for binary 0 and another voltage level for binary 1. Polarity refers to whether you have a positive or a negative pulse. Right. So unipolar encoding uses only one polarity. It will use only one polarity, either positive or negative. So this is a bipolar or bipolar kind of system. But let us concentrate on the unipolar strategy first, where the polarity, of course, refers to the positive or negative pulse. Unipolar encoding uses only one polarity. Only one of the two binary states is encoded, usually the one. Meaning by that we will allocate a certain amount of voltage to one, either plus 5 volt or minus 5 volt, and 0 to volt to 0. The two problems. So this is the exam. This is the graph for uniform polar coding. Now there are two problems associated with this type of coding strategy. One is that it will have a certain amount of DC component, and there will be synchronization problems from the synchronization between transmitter and receiver. What is the meaning of synchronization? That the bits transmitted in a particular symbol period. So in when these are received at the receiver, in that particular symbol period, only those bits which were put in that symbol period should be detected. There should be proper synchronization between the transmitter and the receiver. So that will be a problem in this unipolar encoding strategy. So this is the example of unipolar encoding. So 0 is represented with 0 volts, 1 is with certain positive voltage, and so on. So unipolar encoding uses only one voltage level. What are the problems? As I have explained, there will be presence of DC component in the unipolar encoding. So average amplitude of a unipolar encoded signal is non-zero, because it will have one, because if you look at the diagrams, the average will have a certain amount of average component or DC component in this type of encoding scheme. So average amplitude of a unipolar encoded signal is non-zero. This creates a direct current or DC component shifts the zero level that cannot travel through some media. So the problem is that because we have to transmit the digital bit stream maybe through various types of channels. It can be wired channel, it can be a microwave channel, or it can be a fiber optic channel. So in some media, it is difficult to transmit, or it is difficult that this DC component can be traveled, can be sent, or can travel through some certain type of media. And as I told you that there is a synchronization problem also, the change in voltage for each bit is what allows the digital encoding scheme to indicate changes in bit type. For example, so whenever there is a change in the voltage level, so that will actually indicate whether it is going from 1 to 0 or 0 to 1. So that's what is the meaning of this line. Now so it will be there will be a synchronization problem because the voltage level, it will be more prominent to synchronization to disturbing the synchronization issues in the transmitter and the receiver. Long strings of zeros and ones. So if a bit stream involves long zeros, I mean there can be 1,000 zeros, right? So it will be difficult to to achieve the kind of synchronization required. Long strings of zeros and ones do not produce any transitions in the unipolar encoding scheme, which may create problems in error detection and recovery. So lack of synchronization. So this diagram, this is the transmitted signal, this is the received signal. So there can be problem of synchronization in the unipolar encoding scheme. Now let us look at the polar encoding scheme. Polar encoding uses two levels. One is positive and the negative of amplitude. Now polar encoding eliminates some of the DC residual problems because the average voltage level on the line is reduced. Since we are using positive and negative voltages, so definitely if we try to take the average of the polar waveform, in that case, certainly DC component will be drastically reduced, if not zero. The power to transmit this signal is one half that of the unipolar signal. So this is another advantage, that the power requirement to transmit this type of signal is one half that of the unipolar signal. Now there can be several types of polar encoding. One is non-return to zero, return to zero, and biphase. We will one by one discuss these encoding schemes. So polar encoding uses two voltage levels, positive and negative. So this is the main category, which is polar encoding. Under this category, you will have NRZ, RZ, Manchester encoding, and also differential Manchester encoding. Now let's look at what is non-return to zero. Non-return to zero, a signal is always positive or negative. It never returns to zero. The value of the signal does not return to zero. Either it is positive or negative. So there are two main types of non-return to zero type of encoding. One is NRzl. L means level. So NRzl and NRzi. So let's look at what is NRzl. NRzl signal never returns to zero voltage, and the value during a bit time is a level voltage. Right? It never returns to zero voltage. Whatever is the level of the whatever is the level uh, of the encoded waveform, so that will be treated either as 1 or 0. So this type of NRzl encoding scheme, this is good for short and well shielded transmission paths. In NRzl, the level of the signal is dependent upon the state of the bit, as I have just described, that either it is 1 or 0 will depend on the level of the waveform. Right. So let's look at non-return to zero inversion. So this is I stands for inversion. So NRzi, invert on ones. The voltage level will invert whenever there is one in the bit stream. The transition between a positive and negative voltage represents say 1 bit. Whenever there is a transition between positive and negative voltage, it represents a 1. Provides more synchronization than NRzl because there is a transition for each one bit. So once the transition is there, because the clocking edge will be there, so it will lead to more synchronization. So NRzi, the signal is inverted if a 1 is encountered. Let's look at the examples of NRzl and NRzi. So it is 0, it is represented with a positive amplitude, positive polarity. 1 is represented with a negative polarity. It momentarily it shifts from positive voltage to negative voltage. So it never returns to 0 basically. So 0 is positive voltage, 0 is positive voltage. It can be other way around also, there is no problem. 1 is for negative. So this is NRzl, never return to 0, and the indicator for ones and zeros will be the level of the voltage, level of the waveform. So what is NRzi? So whenever there is a 1, so in this bit stream 1 is here, it will do the inversion. So 0 is represented with this positive voltage. So 1 comes, it will make a transition. It will go on like this, 0 with 0, right? It will go on like this, no transition till 1 comes. So whenever 1 comes, it makes another transition. So this particular this particular voltage from for the first simple period is actually just the assumption that it is positive. It is on the positive side, right? So it makes the whenever there is 1, so it will make the transition from low to high. So again there is 1, it will make the transition, and it will make the transition, and so on. So transition because next bit is 1. It will lead to more sophisticated kind of synchronization between the transmitter and the receiver, because the receiver will keep on knowing that what changes are occurring in the waveform, right? Now, the next type of encoding scheme is the return to zero encoding. So it tries to solve the problem of losing synchronization due to long strings of consecutive ones and zeros. So let us look at what is this encoding strategy. Signal change during each bit promotes uh, synchronization. So signal will be changing during each bit, and that will provide more sophisticated and more advanced level of synchronization. So let us look at the point. So positive voltage is 1, negative voltage equal to 0. All right, signal returns to 0 halfway through the bit interval. So let's look at 0. So it has to be negative voltage. For 0, there has to be negative voltage. So this is my negative voltage. So at half the time, it will return to 0. So that's why this type of encoding strategy is known as return to 0. Whereas in NRZ, it was non-return to 0. If you look at the waveform, it never returns to 0. So in RZ, at half the interval, it will return to 0. Giving a 0 in the form of negative voltage, it will return to 0. Then again, it will remain 0 for next half. And if there is 1, it will go to positive voltage. And it will return to 0 after half the bit interval. It returns to 0, then it is 0, it will go to negative voltage, like this. These transitions can be used for synchronization. These bit transitions at the halfway of the bit interval can lead to a better synchronization strategy. Now there are the next type of encoding scheme is the biphase encoding scheme. Signal changes at the middle of the bit interval, does not return to 0, goes to opposite pole. Now that's the difference between RZ and biphase kind of biphase kind of encoding strategy. Here the waveform, the signal returns to 0 and stays at 0 for half the interval. But here in biphase strategy, signal changes at the middle of the bit interval, definitely, but does not return to 0 and goes to opposite pole. Good solution to synchronization problem. Two types of biphase encoding used in networks. One is the Manchester and differential Manchester. We will cover only Manchester type of encoding strategy in this lecture. So Manchester, this code is a self-clocking code, provides a transition for every bit in the middle of the bit cell. This transition is used to provide clocking. Now let's look at how the zeros and ones will be represented. A positive to negative transition will represent a 0, and negative to positive transition will represent a 1. This is known as Manchester encoding. The scheme is used in Ethernet and IEEE 802.3 compliant LANs. It's a very prevalent and very important kind of encoding strategy used in digital communication systems. So let's look at the example of Manchester encoding, in which a 0 is represented by transition from positive to negative. So there is a transition in the middle from positive to negative, which represents it's a 0. So 0 is represented from a transition from positive to negative, and 1 is represented with a transition from negative to positive. So 1 is there, so it will be negative to positive. 0 is there, it will be positive to negative, and so on. In Manchester encoding, the transition at the middle of the bit is is used for both synchronization and used for bit representation also. I'm sorry for the language here. Actually, what I want to say is that the Manchester encoding is used for both synchronization and bit representation. Now let's talk about the analog to digital encoding scheme. So the signal is analog. So look at this signal here. It is analog signal, and we get a digital signal, which is a basic pulse amplitude modulated signal. It's a digital signal here. So the challenge is to transform potentially infinite values in analog message to digital without losing data. So pulse amplitude modulation samples the analog. So this type of encoding scheme samples the analog signal. All right, samples the analog message and generate pulses based on the sampling. Sampling measures the amplitude of the signal at equal intervals. So you sampling, so you will have the pulses here. So this is known as pulse amplitude modulated signal, analog to digital encoding. So various type of strategies are there. If let's say this is the analog signal, the first type of waveform is the pulse amplitude modulated waveform, in which the amplitude of the pulses will represent um, uh, the ones and zeros and so on. Pulse width modulation, in which the width of the pulse will actually determine the ones and zeros. Pulse position modulation, here the position of the pulse will determine the ones and zeros in the digital bit stream. And pulse code modulation, we do the encoding here, that every impulse amplitude modulation, what happens, you do the sampling, and then impulse code modulation, you do the quantization also. In quantization, you allocate the quantized amplitudes to the actual sample amplitudes, and then every quantized value, every quantized amplitude will be given a code depending on the number of bits that you are trying to stack in one symbol period. So it will be an n-bit code. The n-bit code means it can be a 2-bit, 3-bit, 4-bit, and so on. And if you are using a 2-bit code, there will be 4 quantization level, 3 bits. If there will be 8 quantization levels, and so on. So this is an important aspect of communication system. Actually, this aspect was I mean found out, I must say, or actually invented by Nyquist, in which he was trying to find out in 1928 he was trying to find out the how many bits, or what is the achievable transmission rate through the communication lines. So in that process, he came across with this result, in which in binary PCM, so let's talk about the binary PCM here. We have a group of n bits corresponding to L level. So what is if I represent the number of bits used in the PCM level with n and the number of levels as capital L, so what is the relationship? Number of levels will be equal to 2 raised to the power n. Those many levels will be there depending on the number of bits that you are trying to use to encode one sample value, one quantized value, let me say like that. So n is log of log to the base 2 of L. Signal MT is band limited to B hertz. Signal is band limited, let's say, to B hertz, which requires 2 B samples per second, right? That's what the sampling theorem says, that if the signal is band limited to B hertz, which requires 2 B samples per second, because uh, 2 B samples are there, so how many bits will be there? It will be 2 B into n, because we are using for every sample value n bit, right? So the total number of information per second will be 2 NB, and we must transfer 2 NB bits per second. So that's what actually the sampling theorem says. That's the minimum bandwidth BT needed to transmit. So minimum bandwidth needed to transmit 2 NB bits per second is NB. This is BT is the minimum bandwidth. Uh, that's the finding of Nyquist. That's what actually explains the Nyquist sampling theorem. Actually, the sampling theorem is the result of a reverse, the reverse discovery that he has made. The discovery was that the signal is band limited to B, which requires 2 B samples per second, and he was trying to estimate how many, what is the achievable transmission rate. So to find out the achievable transmission rate, and if you just think reversely, then he came out with an idea that if you sample the signal with twice the maximum frequency component present in the signal, you will be able to recover the signal correctly. And from that idea, for 2 NB elements of information, we must transfer 2 NB bits per second. Thus, the minimum bandwidth BT needed to transmit 2 NB bits. Right? Usually, we define the sampling theorem the other way. If this is the bandwidth, then the sampling rate has to be this. But here, what we say, that's the minimum bandwidth BT. Here, we are saying we are trying to find out minimum bandwidth. What is the minimum bandwidth? When you have to send 2 NB bits per second, right? It is Bt equal to Nb hertz. The point is the same, only you are trying to convey, you are trying to discuss a point from both the angles. Practically speaking, usually we choose the transmission bandwidth to be a little higher than the minimum bandwidth required. All right. We know that sampling theorem also says that it has to be at least twice the maximum frequency component present in there. So this line pertains to that particular aspect, that we try to use a little higher bandwidth, so that of course we also try to use the sampling rate more than twice the maximum frequency component present in the signal. So analog to digital encoding schemes, pulse code modulation is one example. Analog to digital encoding. So how to do the analog to digital encoding? We actually take the analog signal, we apply the PAM, pulse amplitude modulation will be there. Then we try to do the quantization, and then quantized amplitudes will, the signal waveform will be having the quantized amplitudes, and then we try to encode the encode every quantized amplitude with binary information, and that can be transmitted through the uh, channel. So I finish my lecture here about the digital formats and line coding schemes. Thank you very much.